Hey, I'm Tim DeStasio and this is Psychrometric Saturday. We've been talking a lot lately about wet bulb temperature. Wet bulb temperature takes into account the heat that's not only in the air, but also in the moisture that's in the air. And wet bulb temperature is very, very important. Last time we also discussed how if our dry bulb temperature, our wet bulb temperature, and our dew point temperature are all the same number, then that is where the saturation curve is. So for example, if I've got 70-degree dry bulb and I've also got 70-degree wet bulb and 70-degree dew point, then that intersection of those three temperatures is always going to be at the saturation curve. If those temperatures are not the same, then that means that the air is not quite saturated. And the farther that the dry bulb temperature is away from the wet bulb or the dew point, then the less saturated the air is. And that tells us something. It tells us that our air can still hold a little bit of moisture and that there is a potential for evaporation of moisture into that air if those temperatures are farther and farther apart. So the farther apart that our dry bulb temperature is from our wet bulb, then the more potential there is for evaporation. And that is how our bodies stay cool, because our bodies have moisture in them. And when we're hot, when our bodies sense that we need to cool off, it is going to make our sweat glands produce sweat. And as that sweat evaporates off of our skin, there is a cooling effect and it helps us to stay cool. Now, sometimes we're in a really humid environment and the air is really close to saturation. And so those droplets of sweat don't evaporate as quickly. We don't cool off as much and we physically have sweat on our skin. But in other climates, we still may be sweating because our body is telling us to sweat, but because the air is so far away from saturation that those sweat droplets don't really form on our skin as readily. Let's take two different climates, for example. We've got Las Vegas, Nevada and Atlanta, Georgia. Now here are the ASHRAE design conditions for both. In Las Vegas, it's 107-degree dry bulb, so we're way over here on our dry bulb scale, and our wet bulb is 66 degrees. So if we were to plot a point 107-degree dry bulb and then 66-degree wet bulb, we will be making an imaginary line diagonal down, and it would be somewhere around right here. That's where Las Vegas, Nevada is. Now in Atlanta, Georgia, those design conditions are 92-degree dry bulb and 74-degree wet bulb. So we would be somewhere 90, and then we'd have to draw an imaginary line around 74, but it would be somewhere around here. Now, this is why the psychrometric chart is so cool, because it helps you visualize some things that are really, really hard if we just had an app that spit out numbers. Look how much closer that Atlanta, Georgia is to our saturation curve, as opposed to the distance between this dot traveling up the wet bulb line to our saturation curve for Las Vegas. There's a really big difference between where these two dots are in relation to the saturation curve. And what we can say is that the farther that your dot is, the farther that your operating point is from the saturation curve, the more potential there is for evaporation and evaporative cooling. And that leads us to what we're going to talk about next time, which is evaporative cooling and why it's much more effective in climates like Las Vegas, Nevada than it would be in Atlanta, Georgia. But we'll have to wait till next time to talk about that. For now, thanks for watching Psychrometric Saturday.